So 7.4, we're comparing linear and nonlinear functions. So up until this point, the only thing that we've looked at is linear functions. And what does it mean for it to be linear? What does that mean? It's a straight line, okay? So for it to be nonlinear, guess what it's not? It's not a line, okay? So there's certain characteristics about your ordered pairs and about a way that the graph looks that makes it nonlinear. All right, one of our last examples is probably one of the easier examples. Like literally, you look at a graph. Is it a line or not? Okay, and that'll tell you. But the first thing we need to do is really understand what is the difference between the two. Okay, and it really has to do with the slope. If a function is linear, it's going to have a slope or a constant rate of change. Okay, so it's always increasing by the same increments. That's why we can rise 2 and run 1, and then rise 2 and run 1, or whatever our slope is. And we can follow that pattern. Well, a nonlinear function does not have that pattern. It is not a line. Okay, and we'll see a couple different examples of what it could look like. But remember, whether it's linear or non, it's still a function. So what makes an equation or a set of ordered pairs a function? We had like one rule for functions. What has to be in those ordered pairs? Caleb? Every function, okay, in order to be a function, every what? Every input has one output. So one input can't have two outputs. Okay, so whether it's linear or non, it's still a function, meaning every input has only one output. All right, that's still the same. That still applies. All right, so the first thing we're going to do is look at two tables of values. So, you know, each of these tables of values, guys, like basically on the test that you took yesterday, we pulled out an ordered pair, found the slope, the y-intercept, we could write an equation. You can do that when it's a linear function. We're not necessarily doing that in this lesson, though. What we're doing is we're going to actually look at these tables and we're going to look for a pattern or a relationship. If there is one, then it's linear. If there's no predictable pattern, then we know it's nonlinear. All right, so go ahead and side by side copy down these tables, okay? Just right there on your notes, side by side, copy down these input-output tables. Okay, so what we're looking for is a pattern between all of my x values. Now, this could be addition between x, between each x value, or it could be multiplication, okay? But it cannot be a mixture of both. All right, and do you guys see that crazy function that I wrote over there next to the screen? And I'll write it up here too, just so it makes sense on the video. What did I write up there? I said y equals 3 times x plus 3 plus x. I mean, is that a function? No. So basically what we're saying is you can't multiply by x and add by x just because you're trying to prove a pattern. All right, it's either all addition or all multiplication. All right, does that make sense? You can't have both. All right, so you might have been looking at that thinking, what in the world was she doing over there? Okay, that's what I was basically saying in the last class. All right, so let's look at how do I get from a 3 to a 6? Technically, it could be two operations, okay? But because I go from a 6 to a 9, also I know that it's probably what, addition or multiplication? No, it's addition, okay? So 3 plus 3 equals 6, okay? So if I can add 3 to each x value to get to the next x value, then I have a definitive pattern. That means that it is probably linear, okay? But I also have to see what's going on with my y values. So does everybody agree I can add 3 to each x value to get to the next one? All right, so using that pattern, what would be the next x value that's not written on the chart? What would be the next one? 15, okay? So you could actually use this pattern to predict values that are not on your chart, okay? You could even go the other way, all right? So now let's look at our y values. We don't have to be adding 3 to y. It's just with our y values, it has to be the same operation as well. So how could I get from all the way across? So how could I get from 40 down to 32? Just tell me. Subtract how many? 8. Subtract 8, okay? So as long as on the next y values, I can subtract 8 to get to the next value, I do have a linear function. If I have to subtract by any other number, it's not linear. That's all I'm trying to prove here, okay? What's 32 minus 24? 8. So I'm subtracting 8 again, all right? 24 minus what number equals 16? And because it was the same operation, this is a linear function. All right, now it's going to say to explain it. Your explanation is in your work up here on the table that you're showing me. I add 3 to all my x's, I subtract 8 to all my y's. There's my pattern, it's linear. Okay? So now let's look at the next one, the next table. All right, I want you to try to find the pattern on your x's. There might be one, there might not be one, okay? So basically you're just gonna write, are you adding or multiplying, and by what value to get from 1 to 3 to 5 to 7, okay? Go ahead and fill that in. Okay, and what am I doing to get from 1 to 3 to 5 to 7? I add 2. So all you have to do, guys, is right above your table, just write that plus 2. You're filling in that pattern. Now I want you to fill in the pattern on the y values. How do you get from 2 to 11, 11 to 33, and 33 to 88? Go ahead and fill in those values. Hey, how do I get from 2 to 11? Just tell me. Plus 9.
Miss Kinder, can I?
All right, plus 9. 11 to 33. You have to be adding since you added on the first one. Add how many? 22. Add 22. Okay. And then what about the next one? Add 55. Okay. So because I added by different amounts, now it's still a function. I want you to understand that because every input, none of the inputs repeat. So every input has one output. But if you were to graph this on a graph, it will not be a straight line. It does not follow a specific pattern. So it doesn't mean that it's, you know, not a function. It just means that it's nonlinear. Okay? It just means that it's nonlinear. It's got to have that pattern to be linear. All right? Okay? Got it? Example 2. I can actually look at an equation and tell whether it's linear or nonlinear. And here's my criteria. It's got to be able to be written in function form. This was on your test yesterday. What is the template for function form? What's the template for function form? Kayla? Got it. Y equals mx plus b. So, can I get the equation in that format, okay? So, nothing can be attached to my x as far as an exponent or a square root, okay? That's definitely not going to work. That's not going to be. This is a linear function here, okay? So, what we're going to do is look at these equations and can I get it in that format? If the answer is yes, it's linear. If the answer is no, it's nonlinear. All right, let's look at the first one. Right now, as this first equation is written, it is not in function form because up here, there's no parentheses. Okay, so I've got to use distributive property to get rid of those. All right, so you guys remember how to do that? Okay, go ahead and do the distributive property to rewrite this. So it would be y equals distribute. Are you doing it? Y equals. Okay, what's going to be your first term? 4x. Milani, what's going to be your second term? Very good. Minus 4, because 4 times negative 1 is negative 4. Basically what we did was we distributed the 4. 4 times x is 4x. 4 times negative 1 is negative 4. So is this format matching function form? Yes. So I would say linear. Yeah, because that's in the format. All right, I've got a whole number connected to my x and then my y-intercept. This is linear. This is what I've been looking at all year, these types of equations. Okay? Let's look at the top right one now. Y equals 4 over x. This is different than what we've seen earlier in the chapter, y. Well, we've seen fractions connected to x. But where is x? It's in the denominator. Okay? So what you need to know about linear and nonlinear is when x is in the denominator, and think if you were putting in values in here for x, okay? The output or the y values that come out of it, the ordered pairs, when x is in the denominator, it's not going to be linear, okay? So if you look at a problem on a homework or a quiz or a test, and x is in the denominator, it's nonlinear. X is in the denominator. And it will ask you to explain why it's linear or non. Okay? So on the linear side, you would just say it's in function form. All right, and we can see that. All right, so let's answer the two on the bottom. Y equals x plus 5. Is that linear? And y equals 1 minus x squared. Could that be rewritten and be a linear function? All right, so go ahead and just look at those and try to answer them, and then we'll go over it. All right, so y equals x plus 5. Y equals x plus 5. That's totally linear, guys. I mean, that's like as straightforward as it comes. It's y equals, and then you have your x, and then you have your b. There's not even a fraction. It's a whole number. This is as straightforward as it gets. This is definitely going to be linear. Okay, so we see that what is connected to x in this last equation? What's connected? The exponent of 2. So if I were to try to get this into function form, okay, I could switch them around. Y equals, now my x term is next, and then my number by itself. But in order to get x by itself, I have to take the square root of this side, and then I still have a negative, and then I have to take the square root of the other side, because whatever I do to one side, I do to the other. Basically, what we're saying is we can't get this equation into y equals mx plus b because of the square root. So anytime you see an exponent connected to x, it's nonlinear or a square root, okay? It cannot be written y equals mx plus b. It's impossible. All right, so that exponent connected to x, automatically nonlinear. So this is something that you can memorize, all right? If I gave you a worksheet of 10 equations, all right, and I said, is it linear or nonlinear? You're looking for some of this criteria. If x is in the denominator, nonlinear, can't be. Okay, can't be linear. And then same thing with the exponents. All right, that's just some of the criteria that we can look for. All right, now example 3, which I kind of find it funny when they, you know, I think this maybe should have been the first example to kind of give us a visual on it. But basically what it's asking us in example 3 is it linear or nonlinear? And it literally is it a straight line or not? Okay, all the way through. Okay, so I want you to label them. Numbers 1, 2, 3, and 4. Okay? You don't have to draw them. You could kind of draw the curved part. This is straight from your book as well. You could sketch a quick graph, but please do not worry about the numbering part of it. That would just take too much time. Okay, so number one is obviously what? We can look at that. It's nonlinear, okay? There's no tricks to it. There's no catches. If it's a straight line, it's linear. If it's not, then it's non. What about number two? Is it a straight line? Yep. So it's linear. What about number three? Everybody look at. Okay. Now, would you agree that each side is a straight line? Yeah. But it has to be a continuous straight line. This is not linear. Okay. That's why we put that one on there, just to clarify that. All right, and last but not least, what do you think about number four? Linear. Definitely. Okay. All right, any other questions? Okay, one more slide. Did you know that there are properties, or we could call them characteristics, features, in our eyes that actually help us determine color? Yes. Like when you look at something, we all see, unless is anybody in here colorblind or partly? Anybody in here? Okay. So there are some people who, because of the characteristics of their eyes, they don't see colors the same way that other people do. Okay. So how do our eyes, how do our brains determine that's red or that's blue or green? Well, it has to do with exactly what this problem is talking about, the frequency of a light wave and the function of its wavelength. So I know that gets kind of technical, but basically what it's saying is because of these properties of these light waves, that's what tells us something is red or yellow or blue or green or purple or whatever it is. So here's all we're looking for. On the wavelength and on the frequency, is there a consistent pattern between my values? Okay, whether it's adding, subtracting, multiplying, but it has to be the same operation all the way across. All right, what am I doing to get from 660 to 595 to 530? Is it the same value? Okay, that's what I'm testing. All right, basically to see whether it's a linear or nonlinear function. Okay, so did you know that you could do this actually? Mental math? Mental math, anybody? Okay, 595. Guys, this is so important. We're becoming too dependent on our calculators. I do not want you to use your calculator for this one. 595 is really close to what number? 600. Okay, so I'm just going to kind of like tuck that information away real fast. What is the difference between 660 and 600? 60. Now, 600, all right, so that's 60. 600 is how many more than 595? 5. So what's 60 plus 5? 65. So that's how I know that there's a difference of 65. Okay? So if there's a number that's really close to an even number that's easily subtracted, I can round it up and do that easy subtraction and then just add in the difference. Let's try to do it again. Between yellow and green, we're going mental math on this. Again, what do we say yellow, what value is that really close to? We just said it. 600. Okay? So I want you to subtract it. And now we're going to go 5 the other way. Okay? So give you a second to figure that out. Everybody should be writing this down. It could be 65 or it could be a different value. That's what we're testing. What's 600 minus 530? What's 600 minus 530? Well, you know that there's 100 between 500 and 600, right? If you already went 30, how many more do you need to go to get to 600? 30 plus what is 100? 70. Okay? Now take 5 away from that because you've got to step back down to 595. and it's 65 again. Okay? You say, well, this is ridiculous. I just want to use my calculator. Why do I have to do this? Okay, well, here's my answer to that. When you take your college entrance testing, I'm taking SAT, ACT, but more specifically to determine what math class you start in college, if you have to go to the remedial maths, or if you can start in college algebra, you have to pass a test. And that test, you do not get a calculator for. And for that test, we're talking the level math that you're in right now, 8th grade math, all right? And what we don't want to see is our 10th and 11th graders and 12th graders not able to do 8th grade math because they're so used to using their calculators. Does that make sense? It doesn't mean that you're not smart enough, because you're doing well in those maths. But you can't be that dependent on your calculators, because that test is on a computer and they do not let you use a calculator. All right, do you see that? So I'm kind of trying to get you ready for what's coming. All right? Okay, so if we just subtract all the way across, we are subtracting 65 from each one. So right now, I think there's a good possibility this is a linear function. Okay? So let's go ahead and do the bottom. I'll let you use your calculators. I think I've proven my point, right? So second semester, we're going to be doing quite a bit more review type things without calculators to sharpen those skills. Let's go ahead and just try to find the pattern, if there is one, from red to yellow to green to blue to violet. All right, go ahead and fill in the gaps. How many am I adding by?
79.
All right, so I'm adding 50, and then I add, what's my second one? What's my second one?
62.
What is it, 62?
60.
No, 62. What's my next one?
79.
79. So right now, before I even fill in the rest of it, is this linear or non? It's definitely non-linear, because my y's had to be adding the same values.
Session 1 for the...
Okay, what's my last interval? 104, okay? And then based on that evidence, I'm going to say nonlinear. Okay? There's no specific pattern. All right? And if you understand that, that's everything you need to know for 7.4.